All right. All right. Good afternoon, technically. We are in the second class of this week 14. So we carry on the analysis of the amplifiers. What amplifier we did last time? Common source amplifier. The same as the quiz. Number 7 that we just did. Okay, great. So today, inshallah, we get to the other amplifier, which is the common gate. This is the common gate amplifier. So basically the gate is now grounded, yes or no? It's grounded.
Yeah.
In AC or DC?
In AC.
In AC. So if we had here a battery, it will be common gate or no?
No.
No? Why, Mohammed?
Because they're not all connected.
Be careful with video. I don't want you to rack the camera.
They're not all connected to the same ground. Like they have different values of voltage.
Okay, what do you think, Bilal?
Can you please repeat?
If we have here a battery like this.
A DC source.
A DC source. So in that case, can we call this amplifier common gate or no? Amplifier.
Yeah, we can.
We can? Why?
Because in AC, DC is ground.
It's not grounded, it's shorted. It's shorted. If it's connected to the ground, it will be grounded. The whole thing will be grounded. But any DC is always shorted. And you take it off and then make shorted. In that case, the gate isn't common or no?
Yes.
Common. Do you understand? You got it, Muhammad?
Yes.
It's good to make mistakes. That's the way we learn. Do you understand? Yeah. So clear? Good. So let's move on. So this is what? This is the amplifier with the DC and AC. It's the instantaneous thing. So it includes the bias. It includes also the AC signal. Okay? So the first thing we need to do to analyze an amplifier, we have to convert it to what? To the AC. So this conversion is actually the AC conversion. So in which any DC voltage will become what? Shorted. So this will be shorted, it will be grounded, and that's what we have here. This resistance stays there. This is the transistor, I keep it that way. The VDD is now also shorted. Shorted how? Like this. So actually it's like this, yes or no battery? Huh? Correct? Now shorted, then it will be what? Grounded. So this is this terminal. Do you understand? Good. That's it. And the output is taken from where? What's the terminal here? The drain. Good. So the drain is going to be the output. Bingo. Here we are ignoring the channel modulation. That's in this quiz. Channel modulation is not considered. That means lambda is 0. That's it. Or R0 is infinity. So R0 is not going to be included there. That means the next step is actually to replace the transistor with what? With a model. Yes or no? And in that model, we have taken R0 away. So this R0, which is connecting what? The drain to the source, is now out. Because it's infinity, because lambda is equal to 0. Clear? Yes or no? Are you following me, or you are preparing the next exam or quiz? Yeah, it seems you are doing something else. Good. So please focus with me. Yeah. So this R0 now is out of the picture. So let me delete it. Bye bye. Thank you very much. Good. So let's keep going. Now we have this is what? So we have everything here. So let's see. So the gate. Where's the gate? This is the gate. This is my model. My AC model of the transistor, of the MOSFET that we studied before. So the gate here is connected to the ground. That's true. This is the gate. Boom. And this is the drain. The drain is here. And from the drain there is a current, GMVGS, and R0, which is bye-bye. Okay? And that drain is connected to RD. Yes, it's connected to RD. And the source here is connected to R signal. It's connected to R signal. And there we have this input signal. Bingo. Alas? Clear? Yes or no?
Yes.
So now this is what? This is the AC. The final AC view of my circuit. And this is the view that I need to study the amplifier. Do you understand? Excellent. So let's keep going. So Rn. Rn is actually the input voltage divided by the input current. Clear? Let's go. So the input voltage is this voltage. It's not this one. It's this one. Because here where my input voltage is at the channel, at the terminal. So the terminal here of my signal is going to be this terminal. It has to be either the source, the gate, or the drain. The input voltage cannot be here. This is the input signal. Because the input signal has a resistance that we need to consider. Huh? So the input signal is going to be here at the terminal of the input, which is of the terminal of the transistor. So that's good. So this voltage divided by the current that comes in. Very good. Very good. So how we can calculate this? Can somebody tell me? Okay, what is the input current? The input current is equal to what? Is actually opposite to this current, yes or no? This current, I know it or no?
Yeah.
But I know it is actually GM VGS.
Ah, yeah.
Correct, GM VGS, that's me. And VGS is what? Is the voltage between the gate, so this one minus this one, yes or no? Correct or no?
Minus what?
So VGS is VG minus VS.
Ah, yeah.
Very simple, guys. Keep the same understanding that we learned before. Huh? No twist. So VGS is VG minus VS. VG minus what? VS. VG minus VS. Excellent. So follow me. I'm going to go quickly here. So V input here. So let's see. V input. V input is actually equal to what? V input is actually this voltage referred to the ground, which is the same of this voltage referred to this. Yes or no? True? Following me? This is the ground, and this is the ground, same ground, yes or no? So the voltage from this to this is the same as from this to this, because same ground, yes or no? That's why we call it common. Common what? Common ground. That's the right word. Common ground is the ground everywhere. We don't have two grounds. Got it, Bilal? Cool? Very good. So basically the voltage from here to this ground is same like this one, and this voltage is what? Is actually VGS is equal to, is going to be minus Vin, yes or no? This voltage, this voltage. This voltage is actually VGS. Somewhere following me? True? And this voltage is Vin. Vin is actually this minus this. It's actually in red, it's like this. This is in red, V. Yes or no? Correct? Muhammad, follow me? Yeah. Good, it seems like getting tired after the quiz, huh? So V input here is actually this voltage minus the ground. Correct? Ali, follow me? Good. So that's V input. And VGS is this voltage minus this. So Vin and VGS, they are what? With a minus. They are just reverse or opposite to each other. So Vin is actually minus VGS. As simple as that. Clear? Excellent. So, very good. And the current I, let me put this one back. I input is equal to what? The current I is actually coming here. Yeah. But actually the current that they have on the other side. No, it's not this minus this. This is equal to minus that. Do you understand? Because the current is coming in. I don't have two currents. Yeah. But the current that I have here is actually opposite to the other one. Do you understand? It's equal to the opposite. So I is going to be equal to minus what? GM. Minus GM. Oh, hold on a second. Minus GM. VGS. Clear? Excellent. Now the green. You got it? So VI divided by II is going to be equal to minus VGS divided by minus GM VGS. Oh, thank you very much. So this is going. So the result is 1 over GM, which is the input resistance. Just Bill. Go ahead.
What do you mean by input resistance?
The input resistance is the resistance of my amplifier. The input resistance It means it's the resistance that my input signal will feel, will see.
Okay.
Do you understand? That's it. So that's the resistance. If I send my signal in, we'll find. That's the signal, the resistance that is loading my signal. I will find this resistance. Do you understand? It's like fight too. If you are in a, let's say, in a game, like for example of American football, for example. If you have only one, you can push him away. But if you have a bunch of people, it will be very hard. So that's the resistance you will face. Same thing here. The signal is coming in, but you will find the resistance. Electrical, huh? It's a different story. So now that's the resistance, that my signal, my input, not my input signal, the input voltage, because the input signal actually is not here, it's actually here. Do you understand? Just to not mix. Cool? So that's the one. Very simple, very easy. I'm sure some people are preparing other exams, but I need you to focus here, huh? Please. Good. So now we got this very easy. Now this is what somebody revised last time.
Gain.
What's called? Gain. What's gain?
So
What kind of gain?
Without the signal.
Voltage. What?
So there is no signal.
No signal. It's voltage gain. Very good. You are school. Voltage gain. صح. Of what? Voltage gain. What's not means? No, that's not output here in this case. Nobody revised. I'm sure this is a proof that you did not look at the slide. صح ولا لا? Makes sense, Hassan? Hassan, are you with us or not? I just give you the correction, huh? 20 extra points. Then he's lucky actually. But next time, if you don't write the number of the question, I will not include it. Do you understand, Hassan? Clear? Okay. So to be clear. So guys, not means open output. Open circuit. So there is no RL. When I put RL at the output, here, if I put RL, it's going to be here. At the output. RL. Which is the input resistance of the next stage. Do you understand? So there is no load for this gain. Do you understand? Open circuit voltage gain. That's what we wrote last time. Clearly? Good. So, to calculate this, I just make this trick. V output divided by I input, multiply by I input, divide by by the input voltage. Because I can cancel this with this. Yeah. But why I do that? Well, because it's easy. V output, hold on a second. This guy, I divided by VI, is actually this reversed. So 1 over Gm, easy. Now, V output divided by I input, this is RD. Oh, why is that? Let's see. V output divided by II. Actually, we should have swap this guy with this guy because this is taken from here. So, what is that? Is the output here, the output divided by the input current. When I have basically grounded the input voltage, which is here. So if I, let's see. Yeah, so if I ground the input voltage, which is actually this one. What's this? The definition of this is actually R out. Okay, this is the output resistance, which is calculated like what? The output resistance is actually, what's that? Hold on a second. V out over I input. Let's see. V out over I input. It's actually the same as that one. Okay, good. So let's see. The definition of R out is actually V out, or actually Vx, over Ix, yes or no, when V input is equal to 0. That's what we did last time, remember? Yeah. Very good. So Vx over Ix is actually means that I send here a current, Ix, and I measure the output voltage. When the input voltage, where is the input voltage? Here, the input voltage, here, this one, not this one, this one is grounded. Okay? So when I ground this guy, so that means, when I ground, that means Vi is actually equal to 0. If Vi is equal to 0, Vgs is going to be 0. And in that case, this is going to be open circuit, yes or no? So there will be no current coming here. So my Ix will not go through this branch, will go only through this branch. So the output resistance is going to be only RD. I repeat. Again? Last time, we don't have much time. So, here, the output resistance, to calculate the output resistance, we have to ground the input voltage, which is this one.
Yeah.
If I ground this one, that means this voltage is going to be what? 0.
Yeah.
This is 0, this is 0, VGS is going to be equal to 0. If VGS is equal to 0, the current here, GM VGS, is going to be also 0. That means this branch is open. Yeah? Very good. So my current that I will send from the output will not go through this branch, will go only through this. And that resistance is what? RD. Bingo. That's it. So in other words, V out divided actually here in this case, then the output voltage divided by the input current. Here I have to explain further. I will try to make the change of the slide. V output over the input current is going to be equal to RD. It's the same as this one. RD is going to be the same as Vx over Ix. But we can explain it later on. But take it as this. I will try to change the slide later. So multiply this by this, we get GM RD. Okay. R out is already discussed. So the last characteristic is going to be the overall voltage gain. So it's the output voltage divided by the signal voltage, which is this one. So applying the formula that we studied last time, so we can basically get the following. Okay, so what is this? Let's see. So V out over V signal is going to be equal to, let's see, we have V signal here. So we have to, okay, so here this guy is actually with this guy off. So basically we are stretching this guy and put VI on top on the bottom, numerator, denominator. We have VI, and we have V out, which has to include RL, okay? So here V out is including RL. So this divided by this, what is it equal? The input voltage over the input voltage divided by the input voltage. So you can see this is also a voltage divider. So V signal is equal to what? V, hold on a second. There's one little, one little issue here. Okay, for this one is very simple actually. Here, this is equal to what? It's going to be equal to this. But how do we find it? It's very easy. The input resistance, looking here, is actually what? It's actually 1 over GM, yes or no?
Yes.
So this is what? Rn. Yes or no? This is also Rn. So here, V out, V in over V signal, we have just applied the voltage divider that we talked before. Is going to be Rn over Rn plus R signal. Okay? So here is basically we can replace the whole thing by just what? Another resistor here, which is Rn. The same like we did last time. So applying the formula that we studied here, basically here, if you go back, let's go take you back because it seems that you forgot that. Where's that? Here, which is this one. So the overall voltage gain is going to be Rn over Ra plus R signal AV naught. That's exactly what we did there. Just I'm trying to explain it, taking a long time to explain that. So that's exactly what it is. So Rn divided by Ra plus R signal is going to be that conversion multiplied by AV naught. Okay? And that AV naught is going to be equal to what? So now in this case, we don't have RD only. We have also what? RL. What's that RL? Let's see. It's going to be here. What's this? Let's see. RL is going to be here. So it will be RL in parallel with RD. Okay? Multiplied by GM. Okay? And that's gonna be the voltage gain. Because here, the voltage gain here including RL, so instead of RD we'll have to put RD parallel with RL. That's all what we the voltage gain including RL, okay? So instead of RL we will have to put RL parallel to RD, and that's gonna be the voltage gain, not of the open circuit, the voltage gain including the load resistance. Alas? So this is what it is, okay? We need to keep going. Now almost there. The last, so we grounded we grounded the source, we grounded the gate, we need to ground what? We need to ground the drain. That's true. And for that we have to introduce you to the voltage buffer. the voltage buffer or the common drain amplifier, which is in this case, common drain amplifier, is called also voltage buffer because it buffers the voltage. I'll tell you why. It's also called unity gain amplifier because its gain is actually is equal to 1. Okay, so it's voltage over voltage, of course. This is the type of this amplifier. It's very, very interesting, very important. And this is their configuration. So basically, they are well known for one fact, that is, the input resistance has to be very, very small, okay, which is in this case defined as RL for the amplifier. The amplifier is going to be here. And the output resistance, which is this one in this case, refer to the same model that we studied before, is going to be as high as possible compared to the load. So this need to be as high as possible, output resistance of the amplifier. And this is the amplifier, okay? And the input resistance need to be as small as possible. Okay? These are the major characteristics of this amplifier. And obviously, the overall the gain of this output the open circuit voltage gain is actually equal to 1. So it doesn't amplify, but it does make sure that the voltage at the input will be transferred at the output regardless of the load, okay? And regardless of the input resistance of the signal. But the condition to have this, you have to have a very high output resistance for this guy, and very high output resistance for this, as high as possible, and very low input resistance, okay? The other way actually. The input resistance very high and the output resistance very low, okay? Compared to the resistance of the signal and the load. Unfortunately, we don't have much time, but we can discuss it again later on, okay? So this is basically the configuration of the common drain amplifier. So the previous one, just an introduction. So in this case, we have the drain of the transistor is going to be connected to the ground. Of course, in AC version, that means usually this is connected to a voltage, VDD or something like that, okay? So when we transfer the circuit, let's bring this down, let's see. Okay, as you can see here, it's actually, we have already started with the AC view, okay? So where's the signal coming from? The signal needs to be coming from the gate, okay? So the gate now is the input, okay? And the output where is at the source, and that's why we call it also the source follower. And this kind of circuit, they are called source follower. They are used mainly in the active pixel sensors, okay? Where the active pixel sensors, you find them in the image sensors or the cameras, okay? All right, so now in this case, what do we have? So basically, we can have the equivalent circuit first. So we have these things are the input, they don't change. So here, we are using a special configuration for the transistor, and this we call it the T model. We'll come to this model maybe next week, maybe sometime down the future. So in this T model of the MOSFET, what we represent basically the input resistance, because here we are looking at the source like we did last time. We found out that the input resistance looking into the source is equal to 1 over GM. So we have to remember this very clearly. So now I can basically put the resistance here from the source towards the drain equal to 1 over GM, okay? And the current, the total current coming from the drain has to go down the source, okay? So now the output, where is the output? The output terminal is at the source, okay, which is here. So it's here where I can put basically the load, okay? So now, to characterize now the amplifier, the first thing, because the signal is coming to the gate, the current coming in is equal to 0. Therefore, the input resistance is going to be infinity, like we did with the, which one? The common source. Yes or no? Very good. So the first characteristic is very easy to find. Now the second characteristic, let's look at first the output resistance. This is much easier. The output resistance is basically the resistance looking into the source, okay? And that resistance is nothing but 1 over GM. We already found that from the previous slide. So finally, we have to find basically the open circuit voltage gain and the overall voltage gain. So to study the input, open circuit voltage gain, what we do, we put basically a resistance RL. We cannot really avoid RL. Why? Because the current here need to go somewhere. Okay? We cannot take this RL and say I can do analysis. No, I have to put RL there. But then in the analysis, I have to assume RL to go to infinity, because that's called what? This is called the open circuit voltage gain. Means without the effect of RL. So you have to calculate the voltage gain, taking RL to infinity. And the voltage gain, looking at that point, is actually, you can also prove it. We can discuss it next time because it's almost over now. Is equal to RL divided by RL plus 1 over GN. It's basically makes sense because if you look at it here, this, actually we can discuss it now. This is the input voltage, yes or no?
Yes.
From this point to this point. And the output voltage is actually from this point to this point, yes or no? This is nothing but the voltage divider, yes or no? So it's going to be RL divided by this plus this, yes or no? Very good. Now when RL goes to infinity, this will be neglected compared to this, and RL over RL is going to be equal to 1. And that's why we have a unity gain amplifier, okay? The gain is equal to 1. Why the overall gain is the same as the voltage gain here? Actually, this is the voltage gain, not the open circuit one. The open circuit is this one, okay? But the voltage gain, including RL, is going to be equal to this. Why? Because, you know, here we have RL, and that's the voltage gain. This is number 1. Number 2, as you can see, the input voltage is the same as the signal voltage, yes or no? So the voltage gain is going to be the same as the overall voltage gain, yes or no? Because the input signal is the same as the input voltage, that's it. And the output voltage is including RL, so they will be the same in this case, and this will be their values. And when you take RL to infinity, that's what you get. You get a unity voltage gain. Of course, voltage over voltage. That's it. So as we said from here, we get that. So it's the same result. Almost there. This is basically the summary of the different characteristics of all the amplifiers that we studied. Common source with RS, which is today's quiz, today's homework. Common gate and the source follower that we studied at the last time. Okay, that's it. And this concludes chapter 5. You can read the summary at home. Okay. All right. The final thing about the MOSFET as an amplifier to be used as a switch. We already talked about that. For the switch, we have to use our amplifier first when the MOSFET is off or when it is in RF. We studied that where during the study of the VTC, the voltage transfer curve, and in that case, you can use it as a digital logic. Okay, that's it. So as an amplifier, we studied that. So there's nothing really we add. We have seen all these things. So I leave you with that, and see you inshallah next week.